Okay, we now move to the magnetic field associated with solenoids. Before we start, let's work out what a solenoid is. A solenoid is when you take a wire, a single straight wire, and you bend it so that it has loops after loops after loops together. And as a result, you get a cylinder end on. You see this a whole lot of wires, and a current goes in one way, and then current exits the other, and we have a cylinder of coiled wire. So we'll get back to exactly the structure of a solenoid in a few more moments, but just so that we can start with understanding what this word is. Often the word electromagnet is associated with this. So when we, let's write that magnet, when we talk about solenoids, we normally talk about electromagnets at the same time, because an electromagnet and a solenoid can be the same thing. Right, now the last lesson we were looking together, we had a look at the electric field around a conductor. So here is our very thin, straight conductor, and the current is moving in this direction. Let's make it go that way. As a result, there is a circular magnetic field around this conductor. And if we use our right-hand grip rule for a straight conductor, and our thumb, there's the thumbnail, points in the direction of the current, and here is the fingers, and our fingers point in the direction of the circular magnetic field that is surrounding our straight conductor. As a result, that means the circular field that's around this straight conductor would be coming out. So we use dots of the page on top, and for every coming out there would be a going in the other end of this half circle loop. So these become a circle. So in 3 dimensions it would come out of here and into there, go behind and come back. I might go a different colour for the next one. So it comes out, down to there, goes behind and comes back, and so on each time. Just getting one last one, and then behind and back. And we use the dots and the crosses to make it much easier to represent these fields rather than doing 3 dimensions like I've just been drawing. Now there are, the next set of dots would be further out there, and then there will be crosses for those ones as well. So normally we do a couple of rows of dots and a couple of rows of crosses as well. Now that's a straight conductor. Now if we were deciding that we want to bend this in some way, so let's bend our conductor now. So let's put a conductor which is a very generous loop like this, and the current is going this way as well. All we need to do is take any point. So let's just take this point up here and work out the direction of the current at that point. If the current is going out this way, then the current must be going in this way, around, and at that point there the current is going that direction. Using our right-hand grip rule, this time using the thumb this way, and this would be the back of the hand now that we'd see. And that one there, our fingers would be bending forward, and so therefore they would be going into the board up here at this point and out of the board there. Let's take a point over here, doing the same thing and drawing that. If we're going to do our right-hand grip rule again, the thumb is there, so we would be going out of the board on this side and in here. And we can keep on doing this around. You might do it over here, doing it this way. Once again, we would find that it would be out of the board on this side and in here. Okay? So if this was a loop, a full circular loop, rather than a generous loop like that, it would be all of the dots would be inside, and all of the crosses would be outside. So when we have a look at doing a circle, here's our circle, and if the current, we'll keep the current the same way for the time being. If the current in this circular loop goes that direction, then all of the magnetic field would be going directed into the board inside the loop, and it would be directed out of the board around that way. It'll be directed out into the board outside. And if we were to go the opposite direction, so if we have, let's try this one, and we draw it this way, if the current was going that way, and then using your right hand grip rule one more time, so let's draw our right hand. This time our thumb would be pointing this way, and our fingers would be going this way. There's our fingernails. There we are. And that would mean that the magnetic field would be coming out up here and going inside. And no matter where you selected it, the same thing would happen. It would be going into the board inside, and it would be coming out the outside of it. Now that's as if we have a single loop. But if we were to put a whole lot of loops together, then so this is a 3 dimensions, this is one from your textbook. This has a single loop coming in through a plane. And there, if you have a look that enters this plane, then you would get, using your right hand grip rule, you'd get a circular pattern going around there. Now, because it goes down the other direction, the pattern will reverse. The direction of the magnetic field is reversed. And as a result, type of pattern of magnetic field with a single loop. So it would go, one direction is in and would be out. So the direction of the magnetic field through here in the center, I'll use a different color, would be with this direction. So magnetic field is that way, but outside about here, it's that direction, and this one here is also that direction. When we put a whole lot of loops together, these magnetic fields that we see over here combine. So I'll just complete this. So all of these, that single magnetic field around that wire will be combined into a whole series of magnetic fields. And as a result, they have this shape here. And we notice that in between, inside the solenoid, we get a constant magnetic field. We have to be deep inside the solenoid. So we notice that around here and around here, the magnetic field isn't that constant, and around here, the magnetic field is reasonably, the actual lines, the field lines are nice and parallel and constant. So inside a solenoid, deep inside a solenoid, we can actually say that the magnetic field is reasonably constant. Okay? So as a result, using Amperes' law, now we know that from Amperes' law from last time is that B equals mu naught I on 2 pi r. This is the magnetic field around a straight conductor. But if we combine a whole lot of I's and a whole lot of circles together, we get the this expression up here. Now, what are these values here? Once again, B is the magnetic field strength. Mu is the same constant, the magnetic constant from before. And N, however, is the number of loops. So it's not the North Pole here. Please don't think that one. N is the number of loops. So N is the number of loops. Sometimes used as a lowercase n. I, once again, is the current, and L is the length, sometimes used as a lowercase l, as you can see here. So the length of the solenoid is from the first loop to the last loop there. So we know that using Amperes' law for the solenoid, it is proportional, the magnetic field is proportional to the number of loops. it's also proportional to the current. So the stronger the current, the greater the magnetic field is inside our solenoid. And it's also inversely proportional to the length. Okay, so the shorter the length, the less the field, the longer the length, the stronger the field. Okay, it's a pretty simple formula to use. We just simply apply it. And it is designed to find the magnetic field strength inside the conductor, inside the solenoid, okay, and deep inside. Notice it does get slightly constant out here, but it starts to weaken quite rapidly. So it's only to do with the length of the conductor, the number of loops, and the current. Okay. Right, we're now looking at your first of your activity, which is set 78, which is the magnetic field around solenoids. This is question 1, and remembering we're going to be using, I'm going to introduce you to the right-hand grip rule for solenoids now. When you've got a single loop, then we simply use the straight conductor, grip rule, okay, to find the magnetic field. And the way we do that is we just take a single point on, this is the current, we take a single point anywhere, let's put it here, and we pretend at that point there that the loop is straight. And then we use our right-hand grip rule for a straight conductor for a single to work out the magnetic field around it. So at this point here, the current would be going in this direction. Using your right-hand grip rule, you would use thumb there, and that would mean that it would be coming out of the board here and into the board there. Inside the loop, all of the magnetic field is going in, and outside the loop, all of them are coming out. So we know that in a loop, a single loop, all the magnetic field inside is the same. So if it's going into the board inside, all of those will be X's. If it's out, coming out of the board outside the loop, then all of them, no matter where it is around the loop, would be the same. To determine the magnetic field around a solenoid, we use the right-hand grip rule for solenoids. So this is the right-hand grip rule for solenoid. Now, don't get these two confused. The right-hand grip rule for solenoid, this time your fingers, okay, I'll draw a thing again. There is the hand. There is the thumb. Okay, and there's your fingers. This time your fingers point in the direction of the current. Okay, and your thumb points the direction of the North Pole. Okay, in other words, it tells you the direction of the field lines through the solenoid. So looking at this single solenoid here, this one here, we have the current is coming out here and going in here. So the direction of the current is down each way. So your fingers are in this orientation up here. So you've got your fingers coming down. So you have one finger there, another finger there, and your palm would be behind and your thumb would be pointing this direction. So this end would be a North Pole, and this here, which is the flat part of your thumping part of your palm, would be the South Pole. So I just want to run through that one more time so you've got me. So rubbing that out. Now don't forget, this is not the right-hand grip rule for a straight conductor, this is the right-hand grip rule for a solenoid. In this case, your fingers are bent in the direction of the grip of the current. So the current, in this case here, is going on the front. So it's going down this way, then behind that barrel. Okay, so direction is out in front and up behind. So as a result, our fingers are pointing this way, and our thumb, oops, that's a very big thumb, okay, and our thumb points towards the North Pole. So there's our fingers, yep, and that means that this is the south. So that means we can determine that this is the South Pole and this is the North Pole. Okay. Looking at this one, the second solenoid here. Now remember, a solenoid is just simply a coil of wire. This coil of wire has been wrapped around a barrel, a hollow barrel, so that we can see that the direction of winding. This time the current is going in this direction, so current is going in and up there and coming out here. So the way this solenoid is wound is it's going up and then behind is coming down. So in that case, we would have it going up this way and then down behind. Okay, so, and the barrel is in here. Okay. As a result, we would take our right hand grip rule now, and we want our fingers to be gripping into the board. Okay, so we'll be seeing the back of our hand. Okay, so whoops, there's not the back of our hand. Yes, try and do the back of our hand. Okay, and our thumb would be pointing in the direction of the magnetic field. So there's the back of my hand, and there is my thumb, and that would mean that the field lines going through this one would be going this direction. Okay, and the field lines would be pointing, this would make this the North Pole and this would be the South Pole. So the thumper part of your hand is south and your thumb points to the direction of the north. If we were to put these two, let's just clear a few things away. If we were to put these two solenoids together, we would have a South Pole in this position, a North Pole there, a North Pole there, and a South Pole. These two solenoids are electromagnets now, once the current is going through them, and that means that they would repel. So they would, you have two North Poles together. Okay. If you could just pause the video now, and can I get you to do question 1 through to question 5 on set 78, and then come back to me when you've done those. Okay, welcome back. Now we're going to have a look at doing the mathematics using the Ampere rule for the solenoid. This is Ampere's rule for the solenoid, and it's quite simple. We just plug in all the numbers. So here is our example. So a 25 centimeter long solenoid has 600 turns of wire. So we'll pretend that this is our solenoid here. Let's get a pen up, and it's quite many turns. There's 600 turns here, and it is 25 centimeters in length, and the number of turns equals 600. There is also a 3 amp current going in and a 3 amp obviously coming out. Okay, what would be the magnetic field deep inside? Now, because the magnetic field, I'll just drawing these are the wires at the top. There's 600 of them, and there's also 600 wires at the bottom. Okay, so what I've just drawn is I've drawn those set of wires there, and these set of wires here, and they're just forming these. As if I've cut the entire solenoid in half. Now, if we'll just assume that the current is coming out of these and going into there. So if it goes out this way, if all the current is coming out through these ones and going in through those ones, your fingers would be going this way and your thumb would be pointing that way. Okay, so your fingers would be gripping forward and gripping back. So this would be the North Pole and this would be the South Pole. But deep inside this solenoid, the magnetic field is constant. And as a result, the field lines passing through this are equispaced and do not touch, and they're parallel to each other. These would now start to bend back and around once they come out. But deep inside, in here, between the center of the solenoid, there is a magnetic field strength here, which is constant. So if it's here, or here, or here, it doesn't matter where it is, inside here, you have a constant magnetic field. And we're asked to find that magnetic field. So let's just use our values. So B would equal mu, which was 1 point, I've just lost it. Give me a few seconds to, I'm just going to pause my values. Okay, it's 1.257 by 10 to the minus 6. Couldn't remember that part. And the number of loops is 600. The current is 3. And the length is 25 centimeters, which is 0.25 meters. Everything must be in meters and amps for this formula to work. Take a few moments now just to calculate that field strength in the center of the solenoid. And I have a value here, I hope you agree with me, of 9.05 by 10 to the minus 3 Tesla. Okay, they're quite reasonable, they're quite straightforward, this formula. It's just simply placing in the mathematics and doing it. Can I get you now to do question 1 through to question 5 of set 79? Thank you very much.